Today we'll be working on the following problem. Let's assume X is a non-empty set and a mapping from the power set to itself. The power set means the set of all subset of X. And this F has a monotone property, which means like if A is a subset of B, then the image set F of A is also a subset of F of B. Now we want to show that F has a fixed point. This means like there exists a subset of X such that the M is equal to the image set F of M. Okay, pause the video if you want to work on this problem by yourself. All right, let's prove this. So usually, like this kind of problem, like we want to show there is a fixed point, right? So we basically have to construct some set of some sort of a property. So in this case, F is definitely a subset of its image set F of M. So let's see if we consider this set. We construct this Q is, so let's collect all the subset of X such that E is a subset of its image set, right? This is clearly a subset of the power set of X, right? So the power set. And now we want to see, we were going to prove this F has a fixed point by applying the Zorn's lemma, because usually we want to find the existence of such property. So consider this, and Q is a partially, so first partially ordered set by under this inclusion, right? The set inclusion is partially ordered. And now we want to see, like, in order to apply Zorn lemma, we need to verify first Q is not empty. Why? Because the empty set is a subset of anything, so it is also a subset of the image set, right? So which means the empty set itself, it is in Q, right? Because empty set is subset of this. So now we want to show, like, we want to have that for example T is a subset of Q, and then T is a chain. So which means it's a totally ordered sets, right? So T is a subset of a Q. It's a chain. So we want to find a upper bound of T in Q. Then we can apply the Zorn lemma to Q to find the maximum number of this. And then later on, we are going to show this maximum element is actually the one we're looking for. It is the fixed point. So let this the bigger T is in Q, right? So now how do we find the opposite? So we define, naturally, we think about this as is the union of all the sets in T. Remember, T is actually, the member of T is actually a subset of X, right? Because the nature of we with the nature of Q, what we define is actually a subset of a power set of X. So we define this as is S is clearly a element. It's an member in the power set, right? So now, since for all T in this collection of offset, the bigger T, so we have T is a subset of S, right? Because S basically you union everything. So now, because T is T, the bigger T is a subset of a Q. So T is in Q, right? T in Q, meaning like because Q is the collection of all T is a subset of F of T. Remember, T is a subset of X. So which means, but then also we apply the remember this monotone property, right? So if T is a subset of S, F of T is a subset of F of S, right? So what we show is like for all small t in bigger T, it is a subset of f of x. But S is just the union of all the t, small t in bigger T, right? So this means like S is also a subset of f of S, right? So that is to say, S is in Q, right? So we found but from here, of course, every t, small t in T, as T is a subset of S, meaning based on the partial order, set inclusion. So T is smaller than S. So S is also in Q, right? So we found S is an upper bound of T in Q, right? So we first show Q is non-empty, and also for every chain, the totally ordered sets T in Q, we can find a upper bound of T in Q. So apply Zorn's lemma. We have M is a maximum member in Q. Okay, so M is now we claim M is the one what we're looking for. It is the fixed point. Why? Because since first M is in Q. So what is the definition of Q? So Q is the collection of all this. E is a subset of f of E, right? So M in Q. That means M is a subset of f of M, right? Now M is a subset of f of M. We apply f again. So f of M is a subset of f of M. And now if you think about this, if you think of f of M is a set, right? It's a subset of X. It is a subset of f of M. This implies what? F of M is in Q, right? Because Q is the set of all of this E, for which E is a subset of f of E, right? So then but M is a maximum number. The maximum in the sense of set inclusion, right? It's maximum in Q. Then M must be equal to f of M. Otherwise, we find a bigger one, right? F of M bigger one. So that's it.